Great. So our last speaker before lunch is Dr. Simon Fowler from University of Glasgow. Yes.
Thank you very much. It's lovely to be here. Today I'm going to be talking about, it's going to be quite a high-level talk. We've had some quite technical talks so far today. It's really kind of background and vision talk about domain-specific languages for infectious disease modelling, particularly the sort of requirements that we'd need in order to do that. So this is completely out of my community, so just a quick introduction. I'm a lecturer in Programming Language Foundations at the University of Glasgow. I did my PhD in Programming Language Design back in 2019 at the University of Edinburgh. And the reason I'm here today really is my colleague Jess Enright got me involved in this project proposal that Chris is spearheading on probabilistic domain-specific languages for infectious disease modelling. So I'm coming at this from a programming language design perspective. My main two research areas are firstly in behavioural types. So that's type systems which allow you to have a look at kind of very precise specifications on program behaviour with a particular focus on concurrency, so catching protocol violations. And also multi-tier programming, where I've done quite a bit of work on domain-specific languages for querying data, in particular time series temporal data. So really kind of to set the scene for what I'd like to talk about today, it's worth zooming out and thinking, well, what is programming languages research all about? And I always love this picture here. So this is Margaret Hamilton, and she was a scientist at NASA, one of the earlier computer programmers. And she's standing next to a massive pile of punch cards, which were used to actually program one of the Apollo space controllers. Now, punch cards are perforated pieces of data, paper containing binary data. And this is how people actually program these space systems at that particular time. And the modern day equivalent, sure, we're not using punch cards anymore, but we would still be kind of working with assembly language, which is very, very low level. So really, what is programming languages research all about? And it's about us being able to communicate our intentions to a computer. And what programming languages shine at is abstraction, right? So we want to concentrate on what we mean rather than the low-level details of what a computer should do. Now, how many of you here teach, out of curiosity? How many of you have taken over somebody else's course? How many of you have had opinions on some of the material that was in there? So I've done this recently. I've taken over our programming languages course, and this is a segment of one of the course texts, and it says a programming language must be universal. That is to say, every problem must have a solution that can be programmed in the language, if that problem can be solved at all by a computer. And then it goes on. Now, I have very strong opinions about this. So it really only applies to general purpose programming languages. So these are the ones that you kind of write things, write your web servers in and so on. But it kind of really takes away an entire class of programming languages that we use all the time, right? So we might not want to write a graphics shader in SQL, but I would say that SQL is pretty uncontroversially a programming language. But to go further than that, it's much, much easier to write database queries in SQL than it is to write database queries in C, where you've got to go and do all of the iterating over the underlying data structures yourself. And in fact, with things like query planners, you can actually compile that SQL down into something that does its job very, very quickly and very, very efficiently. And furthermore, there are many other languages, typically those based around formal proof and theorem provers, that are definitely not Turing complete and definitely, not universal in this sense. So really, if we zoom in on this class of domain-specific languages, I've talked about SQL already, but these are programming languages that are not necessarily Turing complete, that are tailored to a particular problem domain. And now, I've talked about SQL already, but we've also got ones like Verilog. Now, Verilog is a programming language that's dealing with hardware design. So we can specify specify our hardware very declaratively, and then use the compiler to go and compile it down. There's also Puppet, which is used for, it's a configuration language, and that's used for, say, provisioning various computers, and then you can, use it to provision enterprise-scale computer networks and so on. And the benefit of all of these different things is that you can write very, very concise code, analyze it for correctness more easily, and often there's also the ability to go and compile it into more efficient outputs. So an example here we've got from the domain of digital signal processing is a domain-specific language called Feldspar. And what they allow you to do is something known as vector fusion, which would then allow you to do more efficient DSP programs. Now, from discussion with my colleagues from epidemiology, really, I've learned a bit about the status quo with infectious disease modelling. And really, we kind of, my views, and I think Chris's views on this as well, certainly, are really that modelling is quite difficult because of the quite complex statistical problems that actually arise from all of these things. Modelling requires expertise in epidemiology and computational statistics, and also computer science. So the people, if you think of the Venn diagram, the people in the intersection of those is quite small. And from that, there are definite skills barriers in getting people trained up so that they can do that. The next thing is that modelling is slow. So models are programmed anew for different research projects. People have their own libraries that they like to go and, libraries and languages that they like to use. And this gives us limited reusability, right? So even if people do release their code, it's not in a standard place, it's not indexable, and even if you did want to reuse things, you'd have to go and write your own adapters, and so on. And finally, a lot of models are opaque, right? Because what we've got is this intertwining of, say, forward simulation code with the actual model underneath. And this makes it difficult to audit models, and it also obscures the modeling assumptions. So this can hinder trust in the results. So the question here is, well, can you do domain-specific languages for infectious disease modelling? And people have certainly made really good inroads here. So there have been some very serious attempts at DSLs for infectious disease modelling. And most of these are declarative, right? So what we would do is we would state the parameters of the model, the state, transition rates, rather than the steps required to perform, say, a simulation. And this is good. This is a really good way of going about it. Nevertheless, I would argue that none of the existing work is quite enough to challenge the status quo just yet. So I'll give you an example of a few. So the first one, I was quite interested to read about Kendrick. And the idea here is that Kendrick is a domain-specific language that splits the program into several different clauses. The first is the model. And what we can have here is the epidemic compartments, we can have the parameters, and also various transitions between different compartments and the transition rates that are used. So here, for example, we've got a standard SIR model, and we're saying that we're transitioning from susceptible to infected at rate lambda and infected to removed with rate gamma. Kendrick also allows a degree of composition. So what we're having here is that we've got two epidemics going on at the same time. So we've got a human epidemic and a bird epidemic. And then via the composition clause, we can show that we've got these two things put together. Now, the composition is not necessarily, to me, from this particular program, the semantics of the composition isn't necessarily clear, but it is in a paper, so you can read about it. It is kind of well specified. Finally, there are two final ones. So there's the simulation, and that actually, the scenario, sorry, and that gives the concrete values for the transitions, gives you things like population sizes. And then we've got the ability to give parameters for the simulation, so number of simulation steps, for example. And finally, some parameters to sort of say how you want the outputs visualized. Another, and I think over the coffee break, various people were talking about kappa. So this is a different approach to domain-specific modeling of infectious diseases. Kappa is a rule-based modeling programming language, and it's inspired by molecular biology. It's a rewrite system, essentially, and in the domain of epidemiology, what we can do is we can have rules like this one on the left. And what this is saying is, if we read this as, if I've got a susceptible person next to an infectious person, then that can take a transition with rate k to two infectious people, right? So what we can see this is rewriting a larger state space based on these different rewrite rules. And the paper, Rule-Based Epidemic Models, that should be 21, sorry, not 11, actually shows quite nicely how the approach extends to various scenarios and interventions like masks, hand washing, contact tracing, and so on, and how this can be specified in quite a succinct way. Okay, so to talk about the last thing, I'm just going to give a very, very quick primer on something from my discipline known as functional reactive programming. Now, functional reactive programming is a paradigm which we can use to specify values that change over time. So we've got this very simple example on the left-hand side of the screen here, and that's basically saying, well, we've got two shapes, we've got a circle and a square, and what will happen is the circle will get bigger while the square gets smaller, and we can overlap these to go and kind of compose them into a bigger shape. And the idea of functional reactive programming is everything is focused around this idea of a signal, right? And a signal of a shape, for example, is roughly equivalent to a function from time to a shape, right? So we can see how these different things change over time. And on top of that, what we've got is an event. Now, an event is a discrete occurrence which can change the value of a particular signal. So an idea here is a button press, and one thing that you could imagine happening with this little program here is, you know, it would continuously kind of resize, so this circle would get bigger, the square would get smaller, and then vice versa. And then once you clicked, you could stop this, or you could double the amount that it would go. And people have actually begun looking at functional reactive programming for infectious disease modeling. And this works quite well because, well, if we think about an individual level model, what are we trying to track? Well, we've got a particular agent, and over time, they are going to go and change from whether they are susceptible to infectious to removed. But on top of that, they might have neighbors around them that might change. So all of these different things are time varying. So the code on the left is from a nice little paper called Frabjus, a declarative domain-specific language for agent-based modeling. And really what this is it's a thin layer over a very popular functional reactive programming library for the Haskell programming language. And the idea is, what we can do is talk about a person. The person has an infection state and it's got a bunch of neighbors, and we define a transition function based on its current infectious state, and then we can go and, you know, in the susceptible state, we can go and, with a constant rate, go to infectious. Once we're in infectious, we can go to removed, and in removed, we're not going to go any further. So this is a particular fairly opinionated domain-specific language, and it's a fairly thin layer over Yamper. But there was a lovely paper, Pure Functional Epidemics, and I think Perolov was actually involved in this, which dives more into the principles and practicalities of modeling epidemics directly in Yamper itself. So I believe Chris earlier was talking about the GEM DSL that he had written. So this came out of a Wellcome Trust funded project. And this is a standalone domain-specific language, but it's within the Python ecosystem, and it's backed by TensorFlow probability. And the idea here is it's much more specialized to epidemics, but also with quite a lot of probabilistic programming involved in it. So the idea here is we've got a declarative presentation of epidemics. So we've got the explicit constructs for states. We've got explicit ways of defining transitions. So here we've got the states, we've got the S, the I, the R. We've also got a transition from S to I and a transition from I to R. But on top of that, we've actually got some first-class support here for probability distributions at the top. So we can sample from the gamma distribution here, for example. And the important thing for the GEM language that the other ones don't have is, as well as supporting forward simulation, GEM actually supports a form, certainly some actual inference as well. Now, GEM is a really good step in this direction, but really, at the moment, it's not compositional, so we can't create bigger epidemics out of smaller ones. And it's not quite expressive enough to handle things like population migration events. So things like veterinary epidemics, where we've got a bunch of different farms, maybe some infected animals go, and so on. So we can't quite do that in GEM just yet. So I think there have been some very serious attempts at DSLs for infectious disease modelling so far. But the common drawbacks really are several of them, especially, the majority of them don't really have any kind of explicit probabilistic programming support. And we also, inference is really important, and we can't do that in most of the common DSLs just yet. And secondly, performance is really, really crucial for real models, but most of these DSLs don't make any claims about performance and really come at it from a language design perspective rather than an implementation perspective. So running a full ABS simulation, for example, might be overkill for something that you can solve in a quicker way. So just to briefly go over our plans for a probabilistic domain-specific language for infectious disease modelling. Now, as I say, nothing's been implemented yet. We're still very much at the research and design phase of this. But roughly speaking, we are looking at a system described by this diagram here. So the first part of the system is a domain-specific modelling language. So I'll talk more about this in a minute, but the idea is for it to be a declarative DSL with support for probabilistic programming. Now, the output of this, we are imagining, will be a probabilistic directed acyclic graph. Common internal representation, I believe, is used in WinBugs. And I think actually getting down from this very high-level description to something so small will be quite a challenge, but we'll see how it goes. The next part is the statistics engine. Now, I think Chris talked a little bit about this earlier on, but the idea here is it will provide implementations of statistical machinery, so probability distributions, sampling algorithms, and so on. And a key technical challenge here is the development of kind of compound Markov chain Monte Carlo kernels. It would be nice to have a monadic or maybe kind of monoidal interface for actually plugging these things together. And the idea with the statistics engine is that actual computational statisticians can plug in modules that they're working on. It can be used directly by people who want to make use of the Python API for what they're doing, but also by the sampling planner, which really, the goal of the sampling planner is to assemble from these different building blocks a suitable training or prediction algorithm from the probabilistic directed acyclic graph that we get from the modeling language. So the idea is that it takes the role of an experienced statistician. And the reason we called it the sampling planner is really by analogy to relational database management systems where we have this notion of a query planner, which can kind of plug things together and say the best way of executing something. And we're envisaging that there will be two main phases in this. So the first will be a model transformer. So this will apply transformations to our probabilistic directed acyclic graph to maximize the efficiency of any sampling algorithms that we're going to use. And then also the algorithm builder, which will assemble different components from the statistics engine. And finally, this will output a sampling program, and we envisage then being able to plug this into standard Python data science tools for visualization and analysis. So in terms of the actual principles that we think are important for the modeling language design is really, I think everybody so far has really got it right with this declarative presentation of the modeling languages. So not intertwining the simulation or the inference logic with the actual model itself. The compositionality is also crucial, so we want to allow larger epidemics to be created from smaller ones, and this is particularly good for things with population mixing. Coming from the programming languages world, what we will do is we'll always want a formally specified language, so we want the syntax, we want the semantics, all rigorously defined, and then we can go and prove properties about the meta theory. And finally, we'll want it to be correct by construction. So type checking can rule out many quite nasty things that would manifest themselves at runtime statically. And we want to use a lightweight type system with quite a lot of type inference to rule out common nonsensical models. So we're thinking that FRP is an appropriate starting point, although it might not work. It might be too complex, but we think it's a good way of starting because of that very intrinsic notion of something being, an epidemic being time varying itself. I think what's really missing here is integrating the probabilistic features into the reactive framework. So I was very interested in Guillaume's talk earlier in hearing about this. On top of this, we'll need, people will develop all of these different ways of doing modeling. So we need to, as well as being domain specific, we still need to go and allow, flexibility in that modeling to allow people to write things which are expressive enough. And finally, we want to be our type system to be unobtrusive. So really, extensive type inference is crucial. Okay, so as I say, very high-level talk about the kind of early plans of what we want to do. But really, infectious disease modeling is hard, and I think a lot of, particularly the inference direction, gives us quite difficult statistical problems. And that requires everybody to be in this very small intersection of epidemiology, computational statistics, and computer science. At the moment, models are difficult to understand and reuse, and we've begun thinking about how we can use these ideas from the programming language design world, in particular domain-specific languages, to do a probabilistic domain-specific language for infectious disease modeling. So that's everything I've got. Thanks very much.
Time for a couple of questions before lunch. Thomas?
So the syntax should stop you saying things that are nonsense, but should there be some kind of semantic checking or like scientific sense checking as well? What would it be like? Should it say this is, you're in a region of parameter space that will generate nonsense, for example?
Yeah, so there is quite a lot that you can do in the type system level to check this if you've got enough static information. I come from the world of behavioral type systems, so there we can do very, very fine-grained checking of, say, for example, does your communication protocol, if you've got a communication protocol, do you actually implement that communication protocol successfully? And there are loads of tricks that you can do there. I think the difficulty is it's a trade-off, really. You want to go and rule out common errors, but firstly, you don't want to rule out, because the perfect type checker, of course, just rejects every program. And then you know that your program's correct because nothing is well typed, right? So it's about getting that nice middle ground where you rule out nonsensical things that you can rule out quite easily, but don't rule out too much, and you still maintain usability of the system.
Guillaume?
I have a question, but the DSPK is generating a probabilistic DAG,
Yeah.
IR generator, and there is a slight tension between the reactive model and generating this kind of
Yeah, definitely.
such as preparedness. So how would you do that?
That is the research. But yeah, no, absolutely. I think we're going to have to, it's a real interesting bit, actually mediating between, well, what is the IR we'll end up wanting? What is an IR that we can actually work with in the model transformation and statistical sense, and actually mediating between them? We are, obviously, this is planned research. We've not got loads of ideas about how to do this just yet, but this is very kind of high level picture on that.
And just to follow up, I was a bit surprised by the middle part, like the model
Yeah.
transformer and algorithm builder.
Mhm.
Why not take the GEM approach and compile to an existing PPL?
I think a lot of the existing, a lot of the stuff that is in GEM already is actually in that bit. Is that right, Chris?
Yeah, exactly. So I guess what the model transformer is saying is, can we spot things like the opportunity to rotate a Gaussian process so that you kind of orthogonalize its variance, taking kind of known decisions on, you can do sort of similar things within the state transition models to try and orthogonalize the parameters from the missing data and that kind of thing. So it's about kind of recognizing those opportunities and modifying the probabilistic DAG in advance of then generating code from an existing PPL to then implement the model. Sure.
Is there a reason why you mentioned interface of the sampler should be monetic? Is there a particular reason why you want it to be monetic?
So I think this was something that you were thinking about with things like Metropolis within Gibbs. So you often want kind of compound kernels, and you're wanting to compose them in such a way that you don't have to think about exactly what the wiring is. I think that's my understanding of what you're. This GemLib bit is a bit more your domain than mine.
If you think about what an MCMC kernel does, it basically takes a chain state and it spits out a new chain state. But along the way, you also want to be able to trace some internals about that sampler so that you can debug it and make sure it's not doing silly things. And so the monadic thing really is about composing those. If you think about the kernel as a Metropolis Hastings kernel that works on a bit of your state, maybe, and then you have something else. So if you think of those as state transformers that take an X and spit out an X plus a result, you need to have some kind of way of abstracting the composition of those functions so that you kind of get a consistent interface. Yeah. So that's kind of where that comes from.
That makes sense.
Yeah.
I want to counter a little bit.
Sure.
When we do this kind of composition, it's usually quite shallow. For instance, we just do a simple, let's say, HMC or MH within Gibbs.
Yeah.
Instead of doing, I don't know, MH within Gibbs.
Yeah.
So,
Yeah.
Do we? I'm just thinking maybe using monads is a bit too high level of an abstraction.
Well, so I guess what if you want to do MCMC, data augmentation MCMC for an epidemic model, because you don't observe the infection transition, let's say, that's always going to be a discrete space. So you are going to have a kind of a multi-kernel sampler. It is going to be a Metropolis within Gibbs. So yeah, you could definitely just have a list of kernels that you apply, and you could iterate over that list and just apply the functions. But why not actually formally express the semantic of a combination of kernels itself being a kernel? It seems to be a very natural monoidal structure that kind of comes out of the type system. So it's kind of, I guess we're just sort of following our noses on.
Yeah, I mean, we played around with it in Jupyter Notebooks.
Yeah.
And it works quite nicely.
Carl.
So I love the idea of a DSPPL like doing a lot of implementation stuff for us, and that in itself having some compute, like generating that PDAG that you can then go and take advantage of in some of the other parts. But how might one integrate, like, what's necessary to have for me to hand you a black box model where I don't show you any of the internals and have it potentially fit a lot, you know, into the rest of this thing? Like, presumably I need to do something that is properly describing, hey, I take SINR initial conditions and I spit out SINR time series or something, right? I need to describe the boundary conditions of that black box to you. Is there, how are you all thinking about that part of the problem as well, right? Like I love the, hey, I give you the transitions and you write the model for me version, but sometimes I'm not afforded the opportunity to do that. I have to give you the black box. And so, like, what do you tell me about, what constraints do you provide to me about the structural surface of that black box so that I can fit in the rest of your thing? And how does the rest of your thing accommodate me handing you a black box that, you know, meets some surface constraints but is not going to give you the PDAG or whatever?
Shall I show the
System, I guess.
Yeah, the gem code, I think, might be the original kind of from there. If you have a look. So, for goodness sake. Sorry.
Maybe a conversation to carry on over lunch.
But yes, there has been, I think the way that it's done in your gem at the moment is that there's a Python interface which actually allows you to kind of, there's an API which you can then hook into in order to do the inference, and then you would specify these things through the API. But yeah, we'll have a look at the code.